Hello everyone, I'm Motoki Kagami from Nara Institute of Science and Technology. Today I'm going to talk about our work Tag Along Virtual Windows, Increase Perceived Resistance and Task Load in Augmented Reality. This work was a joint work with 8 researchers at different universities. Imagine doing a real-world assembly task with AR glasses while a head-following instruction window stays in your view. During assembly, you frequently move your head to check parts. If the window lags slightly behind, you may feel resistance opposing your head movement, even though no physical force is applied. This perceived resistance can hinder interaction, but if designed well, it may improve usability. Today I'll talk about this perceived resistance. Head-following windows have been evaluated across many tasks as assistive UIs and are considered promising for supporting real-world activities. Pseudo-haptics research shows that UI motion can change perception, including sensations like weight or resistance, and effects like the size-weight illusion indicate that appearance can also influence perceived heaviness in AR and VR. Together, these findings suggest that window design in head-following windows can induce pseudo-haptic sensations such as perceived resistance. However, these lines of work are often discussed separately, and especially for head-driven windows, there is still limited research that jointly quantifies perceived resistance and task load in a way that informs design. Building on prior work, our goal is to identify which design factors of head-following windows drive perceived resistance and task load. We quantify these effects and translate the findings into practical design guidelines for head-following windows. In this study, we examine 3 factors. The first factor is the UI type, head-locked and tag-along, which are 2 representative approaches for head-following windows. The videos here show the actual window behavior for each type. In head-locked, the window rigidly follows the user's head motion and is always placed at the same location in the user's field of view. In contrast, tag-along follows the head motion more gradually. The window is basically fixed in the world, but when it is about to move beyond a certain angular threshold from the center of the user's view, it starts following from that boundary so that it stays within the view. The second factor is follow-up delay. This is not a simple lag. It is an AR development toolkit, MRTK3 parameter originally designed to smooth the window's follow behavior. Here we show tag-along with follow-up delay set to 1.0 seconds. On the left, we visualize the recorded head and window motion. Red is the window, and the cyan-purple lines mark the angular boundary where the tag-along window starts moving. With a 1.0 second delay, the window follows much more slowly, almost dragging behind. On the right, from the user's view, the window lags and can drift toward the edge of the field of view. The final factor is window size. This figure shows the actual physical size of the window. We compared the large and small conditions, while medium was used only as a reference condition. These sizes were chosen to represent the smallest and largest practically feasible window sizes in a real-world environment based on the corresponding field of view. For example, we set the visual angle to 45 degrees for the large condition, 27 degrees for the medium condition, and 9 degrees for the small condition. We fixed the aspect ratio to 16:9 and then computed the corresponding width and height for each size. We ran a within-subjects experiment. We manipulated 3 factors, UI type with 2 levels, follow-up delay with 6 levels, and window size with 2 levels, resulting in a total of 24 conditions. Our primary measure was the resistance rating. Participants compared each condition against a reference condition, head-locked, a 1.0 second follow-up delay, and the medium window size, and reported a relative score. In addition, as exploratory measures, we collected raw NASA TLX and a head-gaze relationship metric. Specifically, we computed the yaw angle difference between the head and gaze at each sample and then used the per-trial mean of that difference. This serves as a proxy for horizontal gaze stabilization difficulty or the burden of visually tracking the window. Importantly, we did not use a fixed threshold. We treated it as a continuous value and compared it across conditions. Participants wore a video see-through HMD, the MetaQuest Pro, and observed a virtual window presented 0.7 meters in front of them. They moved their head left and right between markers placed at 45 degrees to the left and right, following a 30 BPM metronome, and rated the perceived resistance of the window. The initial facing direction was standardized and specified at the start of each trial. Before the main experiment, participants practiced moving their head at a steady rhythm to ensure consistent evaluation across participants. The stimulus was a monochrome mock-up of a virtual window. This is a video clip from the actual experiment. The metronome sound was played through the HMD, and participants moved their head left and right in sync with the beat. We analyzed the rating scores using an aligned rank transform ANOVA with 3 factors: UI type, follow-up delay, and window size. The results showed a significant main effect of UI type, with tag-along producing higher ratings, indicating stronger perceived resistance than headlocked. We also found a significant main effect of follow-up delay. Compared to 0.0 seconds, delays of 0.4 seconds, delays of 0.4 seconds or longer yielded significantly higher ratings, suggesting that sufficiently large follow-up delays induce stronger resistance. In contrast, we did not find a significant effect of window size. We analyzed raw NASA TLX using a 3-factor ART ANOVA with UI type, follow-up delay, and window size. The results showed that tag-along produced higher scores than headlocked, indicating greater perceived task load under tag-along. For follow-up delay, scores were significantly higher at delays of 0.8 to 1.0 seconds than at 0.0 seconds and 0.2 seconds. This suggests that adding follow-up delay can increase perceived task load. For window size, scores were higher in the small condition, indicating increased perceived task load. For window size, scores were higher in the small condition, indicating increased perceived task load. We analyzed the gaze head angular offset using a 3-factor ART ANOVA with UI type, follow-up delay, and window size. The results showed that tag-along produced a larger offset than headlocked, indicating that gaze tends to decouple from head movement and become more dispersed. For follow-up delay, the offset increased at delays of 0.6 seconds or longer compared with 0.0 seconds, and we also observed a difference between 0.2 seconds and 0.8 seconds. These results suggest that adding follow-up delay is associated with greater gaze dispersion. For window size, the offset was larger in the small condition, suggesting more dispersed gaze. This is the summary of our results and discussion. Resistance ratings were higher for tag-along, and they were also higher with follow-up delay than with no delay in our tested conditions. Raw NASA TLX and the gaze head angular offset showed a similar pattern, suggesting that the factors associated with perceived resistance and task load were largely consistent. For window size, we did not find a significant effect on resistance ratings, but overall, each measure showed broadly similar trends across factors. Based on these results, we believe that difficulty in controlling the window may have been perceived as resistance. First, tag-along can increase perceived resistance. Tag-along is originally used to make information easier to keep track of, improving situation awareness and accessibility. However, our results show that tag-along can also generate a pseudo-haptic cue in the form of perceived resistance. In other words, depending on the use case, this resistance can be leveraged to emphasize attention and confirmation, for example, in alerts or critical confirmation dialogues. Second, adding follow-up delay can also increase perceived resistance. Follow-up delay is originally intended to smooth the UI motion and improve visual stability. However, our results suggest that, similar to tag-along, adding follow-up delay can also produce a pseudo-haptic cue as perceived resistance. In practice, it can be useful in some cases, such as reducing jitter. That said, tag-along and follow-up delay can encourage attention and appropriate action through perceived resistance, but they may also increase task load. So it is important to choose and apply these settings based on the target scenario while considering this trade-off. For future work, we see 3 directions. First, cross-modality. We want to test whether pseudo-resistance observed with head-following windows also transfers to hand-based control, and whether the underlying mechanism is shared or different. Second, we will strengthen objective measures beyond self-reports by adding behavioral and physiological metrics, such as head motion kinematics and potentially EEG-based fatigue indicators, Third, we will pursue practical validation by evaluating the effects in more realistic UI designs using real content, colors, and layouts to translate these findings into concrete design guidance for AR interfaces. That's all for my presentation. Thank you for your attention.